Good day everyone, we are Group 5 and we will be presenting on Experiment 6, Distillation. First of all, what is distillation? Distillation is a separation method that is used to separate components of a mixture based on the difference in their boiling points. Primarily, you use this if you want to separate non-volatile components from volatile components or simply components with different boiling points. It is governed primarily by two principles, namely Raoult's law and Dalton's law of partial pressures. Raoult's law illustrates the relationship between solution and solvent vapor pressure, in which it dictates that in an ideal solution, the vapor pressure of the solution is equal to the mole fraction of the solvent multiplied by its vapor pressure. In Raoult's law, the vapor pressure of the solution is equal to the mole fraction of the solvent multiplied by its vapor pressure, which is illustrated in the left side of the slide. The second principle governing distillation is Dalton's law of partial pressures, which states that the total vapor pressure of a mixture of ideal gases is equal to the sum of the partial vapor pressures of its components, illustrated on the right side of the slide, in which the total pressure is equal to the summation of partial pressures of each component. Two types of distillation will be conducted in this experiment. On the left side, we can see the simple distillation procedure, which is a separation of a mixture primarily done through simple boiling. The volatile substance, or that with a lower boiling point, is vaporized first and removed from contact with a non-volatile substance, which remains liquid. Collecting the distillates in separate receiving flasks, these are then separated from one another. And usually, simple distillation is most efficient for mixtures in which the two components have a large difference in boiling point.
Fractional distillation works with the same principles as simple distillation. However, it makes use of a fractionating column to conduct multiple simple distillation steps. The result is a more pure distillate. This is usually used for mixtures with components that have a small boiling point difference.
Many types of distillation are widely used for practical applications. Understanding the principles behind it is therefore necessary. Although in organic chemistry, the primary application of distillation is chemical purification, there are actually various types of distillation that are used in multiple industries. For example, fractional distillation is often used in petroleum refinery, in which components of crude oil are separated into its fractions. This is necessary as crude oil raw is not really used in any practical uses. Therefore, its individual components must be separated for it to be able to form more useful products such as kerosene, diesel, or gasoline, among many other products. Another application of distillation is in ethanol retrieval in the fermentation of alcoholic beverages. And lastly, there is actually a developing distillation method called membrane distillation, in which liquid and gas components are separated by a porous membrane. This method has piqued interest for its potential use in desalination and wastewater treatment.
Other types of distillation also include steam distillation and vacuum distillation. In steam distillation, the process is capable of separating water-insoluble volatile compounds with high molecular weights from mixtures with non-volatile components. It is used in isolating tars, oils, and other liquid compounds insoluble or slightly soluble in water at all temperatures. Vacuum distillation, on the other hand, is used for compounds with high boiling points. Two of its important uses are its applications in the petroleum and food industries. It is used in crude oil processing, petroleum refining, and extracting compounds from food products.
What are the objectives of this experiment? The objectives of this experiment first include components of a mixture being separated using two distillation operations, simple and fractional distillation. After that, the efficiency of two distillation operations will be determined, and the results obtained from both distillation operations will be discussed and elaborated on.
In this experiment, our objective was to separate the components of a mixture using the two common distillation operations, namely simple and fractional distillation. Their difference is mainly in how the setup was assembled. To separate the components of a mixture, we first started by preparing 15 ml of an alcohol mixture, poured into a round bottom flask. A boiling chip was also added. The two distillation setup, simple and fractional, were then assembled. The sample was heated using a small flame from an alcohol lamp. As soon as boiling starts, the vapors can be seen to rise up the tube. The rate of heating was adjusted by raising or lowering the alcohol lamp. The rate of distillation was set to 3 drops per minute. The temperature for every 0.1 ml of the distillate collected was recorded. The process was continued until the boiling flask is starting to dry up. A distillation curve was constructed by plotting temperature against the volume of distillate. The number of components in the distillate, their respective boiling points, and the approximate volume percentage of the lowest boiling component were calculated based on the graph. The experiment done can then be used to discuss the obtained results from simple and fractional distillation.
In this experiment, the components of an alcohol mixture containing 7.5 milliliters distilled water and 7.5 milliliters 95% ethanol were separated through simple and fractional distillation. Results showed that at 96 degrees Celsius, 10.9 milliliters of distillate was collected using simple distillation, while a total of 13.5 milliliter distillate was collected using fractional distillation at 98 degrees Celsius.
The repeated vaporization, condensation, and boiling in fractional distillation cause the fractional distillation curve to differ from simple distillation, wherein for simple distillation, only one horizontal tie line was needed to intercept with the two equilibrium curves. On the other hand, the process repeats in fractional distillation, where it continues to convert condensing vapor to a more concentrated one after each repetition, resulting in multiple horizontal tie lines. Additionally, due to fractional distillation producing a pure distillate compared to simple distillation, the distillate was collected at a significantly lower temperature. This presents in the graph wherein the horizontal tie line closer to the boiling point of the distillate.
Based on the simple distillation curve, the estimated boiling point of water ranges from 94 to 95 degrees Celsius, while the boiling point of ethanol ranges from 76 to 82 degrees Celsius. On the other hand, based on the fractional distillation curve presented, the boiling point of water is approximately 97.5 degrees Celsius, while the boiling point of ethanol ranges from 71 to 76 degrees Celsius. However, the actual boiling point of water is 100 degrees Celsius, while the actual boiling point of 95% ethanol is 78.2 degrees Celsius.
As observed in the distillation curve of the fractional distillation, the boiling point of the mixture is lower than the boiling point of both components. This can be explained by deviations in Raoult's law that occurs in real solutions. The water-ethanol mixture follows positive deviation of this law. This means that the mixture has a higher vapor pressure than the ideal, explaining the observed lower boiling temperatures. On the other hand, a water-nitric acid mixture would follow a negative deviation of Raoult's law. This means that the mixture has a lower vapor pressure than the ideal. Therefore, water-nitric acid mixtures would exhibit higher boiling point temperatures than that of its components. The deviation from Raoult's law is a result of intermolecular forces present between the components of a real solution. For simple distillation, the percent ethanol in solution was 41.33%. Percent ethanol recovered is 82.67. However, these values are not reliable, which can be explained by the distillation curve of the simple distillation method. It is hard to determine the exact point at which the distillation of ethanol is complete. The gentle slope in the graph shows that the distillate may have higher concentrations of water in it, lowering purity. By virtue of Dalton's law, we know that the vapor above the solution is comprised of a combination of both ethanol and water. With Raoult's law, we know that the concentration of these components in the vapor is affected by a small fraction in vapor pressure in pure form. The mixture is a 1:1 ratio of ethanol and water. Therefore, a small fraction is pretty much the same. For vapor pressure, ethanol is slightly higher. We can therefore conclude that the distillate collected has a slightly higher concentration of ethanol, as can be inferred from the phase diagram. However, it is important to note that there is still considerable amount of water in the distillate. For fractional distillation, The percent ethanol in solution was 43.33%. Percent ethanol recovered is 86.67. These values are more reliable, which can be explained by the distillation curve of the fractional distillation. The steep slope shows a clear transition from distilling ethanol to distilling water. We can be sure that majority of the first distillate is ethanol.
Fractional distillation is a series of distillations usually done with the fractionating column. The fractionating column contains plates that increase surface area where vaporization and condensation can occur. Multiple plates allow successive vaporization and condensation.
These plates are the reason why, as we go higher up the column, the concentration of the more volatile substance in the vapor increases. This is because the heat gradient results to repeated condensation of the component with the higher boiling point. On the other hand, the more volatile substance repeatedly vaporizes until it reaches the condenser. In the end, we get a distillate that has a higher purity. This is demonstrated on the phase diagram on the right. On the first plate, a 50% ethanol solution would have a vapor composed of approximately 65% ethanol and 35% water. This will rise up the fractionating column and arrive at the second plate, which has a different temperature. Some of the water would condense, while some of the ethanol stay in vapor phase. At this point, the vapor is now approximately 72% ethanol and 28% water. This will again rise up the fractionating column and undergo another vaporization-condensation equilibria, further increasing concentration of ethanol in the vapor. Based on the phase diagram, the distilled ethanol would be around 80% purity. It is possible that this would be higher as the vapor passed through more plates. However, there is a limit to the purity of ethanol that can be achieved.
An ethanol-water mixture always contains about 5% water, as ethanol and water mix to form an azeotrope at that proportion. Azeotropes are a specific mixture of compounds in which the vapor formed in distillation has the same composition as the unboiled solution. Because of this property, simple distillation is no longer readily able to separate the components. As each azeotrope has a specific boiling point, azeotropes are classified depending on their deviation from the ideal phase diagram. Azeotropes in phase diagrams that deviate positively from the ideal diagram and reach a minimum have a lower boiling point than either of its components. On the other hand, azeotropes with phase diagrams that deviate negatively from the ideal diagram and reach a maximum have a higher boiling point than either of its components. The ethanol-water azeotrope is part of the former type, as this azeotrope has a lower boiling point than both ethanol and water.
In determining the amount of solution that can be accounted for from the original 15 ml sample volume, the volume of the distillate collected was added to the amount of liquid left in the flask. The percent loss was then computed using the equation. Percent loss is equal to 1 minus the accounted volume over the initial volume of the solution times 100. In simple distillation, 10.9 ml of the initial volume can be accounted for, and the calculated percent loss is 27.33%. While in fractional distillation, 13.5 ml of the initial volume can be accounted for, and the percent loss is 10%.
This experiment was able to conduct a simple and fractional distillation. It can be concluded that fractional distillation produced a pure distillate, as can be observed from the distillation curves. Together with its low percent loss, ultimately, it can be concluded that fractional distillation is more efficient than simple distillation for mixtures comprised of components with small boiling point differences. That is the end of our report. Thank you for listening.